Okay, guys, welcome. So this is the IEEE MTT Santa Clara Valley chapter technical presentation for the month of March. This is an online only meeting, as you know, for considering the given circumstances. So I have a few slides that I want to show before we go into the technical presentation. So the SCV chapter officers on the ballot for the election for this year, the chair's position, it's going to be Jay Banvait. Vice chair would be yours truly, Utkarsh Unikrishna. Treasurer, it'll be Mr. Tom McKay. And for the position of secretary, we have Mr. Than Tu. So next slide is actually about updates in response to the current COVID-19 pandemic. As you guys know, residents in 7 Bay Area counties are now required to shelter in place and limit social interaction at least until April 7th. The shelter in place order is in effect in 7 counties, including Santa Clara, San Francisco, San Mateo, Marin County, Contra Costa, Alameda, and Sonoma. So residents in these counties are allowed to leave their homes for essential services, activities, and work only. And the source for all this is the ABC 7 News website. So as far as our chapter is concerned, all in-person meetings related to our chapter are canceled or postponed. Our monthly technical meetings and officer meetings, technical meeting like this one right now, will continue in an online or webinar format only until further notice. So if you're on LinkedIn, by the way, we have a hashtag MTT-SCV. So if you follow this hashtag on LinkedIn, you can get access to all our presentations, all our news about our upcoming events quickly. So that's, once again, that's hashtag MTT-SCV on LinkedIn. So at this point, we can start looking at today's presentation, the title of which is Amalga, an alternative to conventional MEMS technology for miniature RF microwave components. Our speaker who will be presenting this is Mr. Sourabh Dhillon. Of course, this is an online only meeting, so we expect it to last about an hour or so, with time at the end for Q&A. This meeting is being recorded. Link to the video and the slides will be made available to all those who have registered. So everybody here will get these links in the next few days. So the talk itself, quick abstract about that. So Xidas, which was formerly Integra Devices, uses a new interdisciplinary miniaturization paradigm for microengineering called Amalga, TM. Moving microfabrication beyond the limits of semiconductor style processing to true heterogeneous integration at the micro scale. Xidas engineers draw from a toolbox of hundreds of materials and processes for producing ultra-small precision sensors, actuators, 3D microstructures, and other products that were not possible before. Using this approach, Xidas is able to produce microscopic devices and systems, starting with high-performance microwave relays and moving into miniature millimeter wave components and routing. So, short biography on our speaker for the day. Mr. Sourabh Dhillon is the co-founder and director of business development for Xidas, a spin-out company from UC Irvine. I forgot to ask, everybody can see my screen, right?
Yes.
Okay. He's the co-founder and director of business development for Xidas, a spin-out company from UC Irvine that offers the next generation of MEMS technology for micro devices. He has a master's in entrepreneurship and innovation from the University of Southern California and a bachelor's in biology and chemistry from NYU. He has 5+ years of business development and venture discovery experience from Timetric and CSSDP Investments, looking at new deep science technologies. So before I hand the proceedings off to our speaker, if possible, please keep your microphones muted. And if you have a question, then you can unmute, ask your question, and then mute after that. So with that, I'm going to stop sharing and Mr. Dhillon will take over. So Sourabh, all yours.
Thanks, Utkarsh. Hi, everybody. Sourabh Dhillon here. Hope everyone's staying indoors and feeling healthy. Let me see. I'm going to try to share my screen here real quickly, and then we'll get started. Okay. Hopefully everyone can see my screen.
Yes,
I'll take silence as a yes. Okay.
Yes, we can.
Okay, very good. Yeah, so today I'm going to introduce you and everyone to Amalga, which is what we call a new miniaturization paradigm for designing, developing, manufacturing microelectromechanical devices and microscopic structures. This is a technology that we have at Xidas, which was formerly Integra Devices. And to backtrack a little further, this is all work that was done out of the University of California, Irvine, that we, once the patent was issued, we moved over into the company. A couple of highlights, I won't talk too much about Xidas, but a couple of highlights on a company standpoint. In 2018, we got the Innovation Award for 3D microsensors and devices by Frost and Sullivan. That is essentially due to the Amalga process I'll be talking about. Same with the Innovator of the Year Award in Orange County, because of the cool stuff we've been building with Amalga, and then also partner with the National Science Foundation to start developing new products. So the way we consider it is we're introducing to the marketplace a brand new way of building MEMS technology. I'll talk about the conventional way of doing MEMS today in some detail. I'm not sure how experienced everyone is with that field, but I'll dive into that and particularly talk about the limitations of MEMS. Because when MEMS really started about 30 years ago, it was quite exciting at the time, being able to use semiconductor processing and manufacturing that you would originally do for a computer chip, and start building mechanical structures with it, and miniaturize a lot of the larger electromechanical devices out there. Very exciting. But over the past 3 decades, the amount of devices that have been miniaturized, there's not a lot. You can really count them with 2 hands. You got your accelerometers, your gyroscopes, your microphones, you got some micro mirror arrays. But you start having to get creative with what it can do. And the reason for that is because there's some inherent limitations with that semiconductor thin film approach, which I'll talk about. Now, what we are introducing is a completely different way of doing it. We actually don't use any silicon at all in our approach. Actually, our tagline back in the day was systems beyond silicon. And we used to say we did MEMS, and then everyone thought we were a silicon company. So we had to say, no, we do micro devices, even though essentially it's the same thing. It's just a completely different way of doing it. And so with this, we can build micro sensors, micro relays, micro actuators, microfluidics, and such. I'm camping on this slide because I want to give a little background as to how Amalga was formed. Mark Bachman, who is the biomedical and microengineering professor out of the University of California, Irvine. He's also the co-founder and CTO of this business. He, 15 years ago, was a MEMS engineer, designer. He was responsible for building the 2 clean rooms at the University of California, Irvine. And he was approached by industry and government agencies to build, a new breed of micro devices, leveraging the MEMS facilities and the MEMS capabilities that they had at the university, at a research level. And he got very frustrated because he'd have to say no a lot of the times, because a lot of these projects, particularly for life tech or let's say for some specialty type of sensor that needed some sort of specialty material, couldn't really do it with what he had available. So he got creative and turned his mind towards, instead of the semiconductor industry, he turned it towards the post-semiconductor industry, the microelectronics packaging industry, and saw that they had made some great progress in terms of precision and what they were doing in their manufacturing. And instead of packaging chips, what if you used that technology to build 3-dimensional devices? And so the microelectronics packaging industry leverages a technology called 3D heterogeneous integration. It's a lot of lamination, pick and place, assembly type technologies. We're leveraging that toolbox and we're using it in a different, unique way to build three-dimensional devices. So let's talk about how that differs compared to how people are doing it now. The conventional way you'd make a small electromechanical device is either through MEMS, the MEMS semiconductor approach, or maybe you're going to use a micro machining, a specialty micro machining approach, or even high precision machining. I'm going to focus on MEMS. That seems to be one of the more popular ways of doing things. But in every situation, on the other ones I mentioned as well, it's a monolithic approach, which means it's very hard to integrate different types of processes and materials into one thing. For example, with the MEMS semiconductor, you're really using various forms of silicon, maybe some other specialty materials. But the way it's done is through really three processes, if you will: lithography, deposition, and etch. And what you're doing is you're building one layer on top of another, etching away and then building another layer and creating freestanding structures. And so this like wedding cake approach, where you build one layer on top of another on its own, just because of that's the way it's done, it has limitations. And one of the biggest ones is materials. You're limited in terms of the number of materials that you can use. And to give you an example, let's say I wanted to use a polymer layer at the bottom as one of the bottom layers, and then I wanted to integrate that with a ceramic layer or something at the top. You would not be able to do that, because if a top layer needs to go into an 800-degree furnace and into an oven, that polymer layer is not going to survive. So because the bottom layers have to survive all of the processes of the ones that go on top of it, you're limited in terms of the materials you can use, as well as you're limited in terms of the number of processes you can use. So now as a designer, someone who's trying to design a new device or component, the box of materials and technologies you have to work with is already limited. This is an example I'll talk about later on, but in terms of relays and creating a MEMS relay, this is something the MEMS industry has tried to do for quite some time over the past 30 years. And there's many dead bodies, if you will, on the side of the road, leveraging this type of methodology for manufacturing. And the reason for that is because the limitation in materials, but also, and here's the next limitation, these layers are very, very thin. So you get what is not really three-dimensional, but I like to call it 2.5D, where it's just very pancake-like structures, and they're very thin. So a little piece of dust gets between your contacts, the device fails, and that's actually been the biggest challenge with MEMS relays, which is reliability. And so that's another big limitation. And then on top of that, you do get a benefit of scale with this, because you're building these in wafers and then you dice them up. But then you got to package these devices as well. And a lot of times the packaging can be quite expensive. So how is Amalga different? Instead of building each layer one on top of the other, we build each layer separately. We build and process each one of these layers separately, and then we align and laminate these layers together. So instead of building on wafers, we actually build on panels. So now we can go to best-in-class manufacturing for each of these panels. We can get someone that's, we can get one layer 3D printed. We could get one layer to be etched. We could get one layer to be laser machined, if you will. Whatever's best in class for that layer, we can go ahead and build that layer with that way. And that optimizes cost, because not every layer needs to be high precision. Not every layer needs to be expensive. For layers that need to be high precision, we can even use the semiconductor, MEMS technologies for that layer. And just like in the panel, bring it in and align and bonds together. And then at the very end, we singulate. And the beauty is, because we're leveraging packaging technology, once we've diced it up, the component is already packaged. Now, there's no longer a limitation in materials, because we can use any material we want. There's no longer material in processes, because we can use any process we want. And there's a lot of know-how and expertise in how to bring these materials together. And that is what was done over the 15 years at the university. Now, this Amalga approach was patented to build micro devices, as well as all the devices that were built at the university, which was about 25 different types of products and devices. And the best way to show the power of Amalga is really to go through some example devices that have been built. So that's what I'm going to do. But I've also focused slightly on microwave and RF for the benefit of this talk. But this is the basic backbone. This is the basic overview of what Amalga is. This chart here really shows the power of it, which is how many more materials and processes we can use, as well as technologies, compared to the other forms of microengineering that are out there. So one of the visions that we had as a company when we started was, MEMS is quite successful. Of course, it's a $18 billion industry and does a very good job at creating now low-cost products. We're not trying to use Amalga to build and compete with MEMS and build devices that they're already doing, but to go after the piece of the pie that has yet to be miniaturized, that MEMS has had a hard time doing. Now, it's a $200 billion marketplace in terms of electromechanical devices, sensors, actuators, relays, millimeter wave devices, microfluidics that have yet to be miniaturized. We're going after that piece of the pie. And I mentioned relays, so let's talk about relays, because that is definitely a product that conventional MEMS has really struggled to miniaturize. There's actually two MEMS relay companies out there right now that have a product. One is Analog Devices, and the other is Menlo Micro, which is actually not out just yet, but trying to go into production. And they build their switch using the conventional MEMS semiconductor approaches, so very thin films and electrostatic actuation. This is a completely different way of building a microwave relay, and we'll walk through that right now. But what that allows us to do is it has a lot of benefits compared to those MEMS switches. And in fact, it's a best-in-class relay in terms of larger electromechanical relays, and then counterparts solid-state relays as well. So as you can see in that 3D see-through model, we've essentially miniaturized a larger electromagnetic relay into the footprint of a 4 millimeter by 4 millimeter by 2 millimeter footprint. That's a very small magnet in there. There's a coil layer on the top. There's a polymer flexure that holds that that magnet in place. The reason why it's polymer, so does not affect the RF characteristics. There's substrate materials that are structural layers, and then there's a high frequency substrate at the bottom that has a transmission line. So the way this works is that coil actuates that small magnet up and down onto that transmission line on the bottom. There's a latching plate at the bottom, and there's a latching plate at the top. So this is a latching relay as well. So once you switch it, once you pulse it and it switches, you need no power to keep it on, and you need no power to keep it off. Now, because this is a fairly large magnet, and there's a fairly large stroke, and when I say large, I'm talking in relation to conventional MEMS thin film processing, we can actually hot switch power with this. So in this video right now, you can see that little magnet moving up and down and providing contact onto those transmission lines. That big stroke allows it that when it's off, we get very high isolation. We get great signal integrity. And as I had mentioned with the large magnets and the thick traces, we're able to handle a lot of power and hot switch a lot of power. So it's truly electromagnetic, even in terms of its actuation. It's just at the micro scale. And this is a perfect example of Amalga and the use of Amalga, where as you see that 3D little relay exploding into all the little parts, each one of those parts is a layer that was processed separately and then aligned and laminated together and then diced up into that small device. And as I was talking about with all the different types of materials that are in this, gold contacts, magnets, substrate material, coil layers, the polymer flexure. It's quite powerful in terms of integrating all these different materials into one product. Let's see what's. So I guess if anyone has questions, they can jump on in or wait till the end. Feel free to ask away. I'm gonna give you guys some more technologies that we did some early work on, leveraging Amalga and some of the capabilities we have here at Xidas that are focused towards millimeter wave type of applications. That relay, by the way, I'll go back.
Sorry to interrupt.
Yes.
So quick question. This is Utkarsh, by the way. So on the relay, like how many, usually on these electromechanical relays, there's a cycle count, right? The maximum number. So what is that maximum number for something like this? Is it comparable to a solid state relay, like which is like pretty much infinite, right?
Yeah.
Or is it more in line with the traditional electromechanical relays?
Yes, good question. So it is in line with a traditional electromechanical relay because it is electromechanical. So those contacts eventually are going to wear out. So it's this one, for example, in the range of 5 to 10 million, which is pretty competitive and on par with what you'll see out there in terms of a PCB mount electromagnetic relay. Yeah, in terms of solid state relays, they're always going to beat electromechanical relays in terms of life cycles. And they're always going to beat electromechanical relays in terms of switching speeds as well. They're just going to be much faster switching speeds.
What about like power handling in terms of RF power? How much power can something like this, for instance, I don't know what frequency this particular device can operate at, but like what kind of power handling are we talking about?
Yeah, so this one can handle actually, in terms of handling, over 100 watts of power. This is a DC to 6 gigahertz relay. It performs at 8 gigahertz too. We're speccing it to DC to 6 gigahertz. It can hot switch about 5 watts of 6 gigahertz signal for about 500,000 cycles. That we're quite proud of, that spec right there. In terms of what's out there, it beats a lot of those components. You know, this is something that Mark will say he's quite proud of. We've plugged this relay into the wall and switched an electrical signal, and it hasn't burnt out like you would imagine another MEMS switch. So it's just it's capable of handling a lot of power. Yeah.
Oh, okay. Thanks.
Oh, one more question about this. This is here. What sort of control signals do you need for power?
छोटा सा हल्का फुल्का रहे ना जरा से नहीं तो नहीं नहीं ठीक है बस
the question is, what type of signal? Control signal?
Yeah. How do you control the switch, and how much does it take any power to control it?
Yeah, so it's a 5-volt signal or 12-volt signal. It's a very small amount of current that you pulse for 1 millisecond. I don't have the current number in top of my head, but it's a quick pulse, and then once it's actuated, then you don't need anything else, and then it's a reverse current to switch it back.
Isolation, how much?
Yeah, so just to give you an idea of RF performance here, at the 6 to 8 gigahertz range, we're at 0.2 dB of insertion loss. We're at 30 dB of isolation. We're at 1.1 to 1 VISWAR is the RF specs.
0.02?
Sorry?
0.2 dB?
0.2 dB insertion loss. Now, while we're on the topic of relays, I don't have any slides on this, but actually I might have some slides on this later on. But this is our first foot in the door in terms of relays and microwave relays specifically. We like microwave relays because they're a high value product. Following this would be a coaxial relay and then a waveguide switch, which I'll show as well, for higher frequencies. Now, the way we'll do the coaxial relay, I'll explain a little later on because it combines this technology with another that I'm about to talk about. And then the waveguide switch I'll talk about later on as well. So we're planning to go full-fledged into switches and relays.
Right now, this is like an SPST.
Say that again. Sorry, you got cut off a little bit.
It's an SPST kind of switch. You have
This one we're releasing to the market this year. We're going to go into production Q3, Q4 this year with an SP, ST, and an SP double throw.
SPD. Okay.
Yeah.
And what's the cost of these?
Yeah, good question. So right now, a single unit price is about $40. That, of course, will go down with quantities. And the reason we chose that price point is because that's typically what a RF microwave 6 gigahertz electromechanical relay, that's PCB mount, is selling currently right now at the lower end. Because we're building these in batch, to give you an idea, and we're building these on panels, the cost to produce these is not a lot. It's about $5. So we can be very competitive in terms of pricing once we build out the production. But for now, we're going to be targeting that $40 price range. Any other questions? All right, I'll move on. So here's some work we've done a couple years back that we've put on the shelf, but I thought I'd share with you guys because, you know, if someone is interested in this, this is something we'd love to work on if we found a project. But it's essentially the ability to embed 3D rectaxial traces inside of printed circuit boards. And the reason for that is essentially a much higher frequency routing. The charts on the bottom, that's not our work. This is just work done with in terms of how well floating transmission lines perform for in terms of a methodology for routing. You know, when you get higher and higher in frequencies, you're limited in terms of the PCB transmission line technologies you could use. If it needs to be high performance, you're just going to use wire. You're just going to use coax wire. And if you're in really high frequencies and you need really high performance, you're going to need to use waveguides. This is a best of both worlds where you're getting high density routing because it's integrated inside of a printed circuit board, and it's very, very high performance, DC to 100 gigahertz. Now, the way this works is it's essentially truly a transmission line that's floating. This one, ours, is actually being held up by a dielectric, and then there's metal walls that surround that that floating transmission line. And as I talked about earlier with Amalga and how we build on panels, and these panels are usually substrates, we can, you know, each of these layers that when we build it are essentially high frequency printed circuit board material, and we're just using and integrating specialty materials like dielectrics and the transmission line and the metal walls, and that's how we build and route these things. So these are pictures. This is work that we have done. Now, if you look at that cross section there, that at the bottom right picture, that is probably the best picture we have to show what it is. This is a picture before the final step, which would essentially create metal walls on the sides of each of those columns there. So right now you're seeing metal walls at the bottom and on the roof, and then you see the transmission line in the middle, sandwiched between two dielectrics. There'd be one final process that would fully surround it. Now, as I had mentioned, very high bandwidth. This is DC to 100 gigahertz, extremely low insertion loss, and no crosstalk, right? So you're getting no leakage of signal from one transmission line to the other because it's being completely surrounded by metal walls. And we use PCB fabrication processes to build this. Now, the reason why we put this on the shelf is because, you know, as a small company, we were initially targeting products that we could build and resell, and didn't have a lot of custom work required, you know, standalone components that we can just keep reselling. With this one, as you would imagine, each system is going to be different, so it takes some custom, you know, each project takes some custom work. So just in terms of our bandwidth, it is something we parked, but if this was of high interest to anybody, it's something we could definitely re-engage with.
Sorry.
Mm-hmm.
Can you expand on what kind of feature sizes you're able to, how small can you make these designs? How many layers can you do?
Yeah, so it's been a while since I've looked at those level of details for this. I can get back to you if you shoot me an email with that question. I can find out and get back to you on it. In terms of feature size, this was the first. These layers that we built right now was the first pass that we did on it. And when you see it compared to a penny right there on the top right picture, that gives you a sense of the size scale of those transmission lines. Any other questions? All right. Yeah, so this is something that now combine this with our micro relay technology. This is how we would do coax switching. So essentially, we would create a transmission line with this. And I don't have a picture, unfortunately. I'm sorry about that, but just use the imagination, if you will. Having a magnet that actuates up and down a piece of that transmission line to create contact and take out contact. So so our ability to create a miniaturized coax switch would leverage this technology, as well as the micro actuator technology from the relay, that magnet that goes up and down, that moves a piece up and down. And with this, the size of that coax relay would be really the thing. The thing determining the size of that thing of that relay would be the connectors. That's how small we could make that relay. So I mentioned coax, and then I also mentioned waveguide. This is something that we've proposed to a satellite company that's trying to do low orbit satellite solutions, and they wanted to go all the way to the 60 to 90 gigahertz frequencies, E-band frequencies. What we offered them is the ability to have an integrated system of waveguide filters and the routing. But then what the key technology here is not just that, it's also the waveguide switch, and that's that circular thing you see right here in this model. And what that waveguide switch allowed them to do is create essentially a what's the right word for this? A sexless transceiver, where they could switch the receiving band and the transmitting band, and what those what frequencies those are at, through this waveguide switch. Now we're able to create floating structures in the waveguide, which allows us to create things like filters and attenuators. So overall, you get a very compact waveguide switch and waveguide assembly overall. And so this is something that we proposed to them as well. And then we actually wanted to put a pause on this project, just because, as I had mentioned, the bandwidth of our company and some of the other projects that we had going on. So this was something else that we parked at the time. To give you an idea, we don't just do RF microwave stuff. We do a lot of medical devices, a lot of medical sensors, a lot of microfluidics, a lot of IoT systems and IoT sensors and energy harvesting components for IoT sensors. You name it, that's anything at the micro scale we work on. We do interposers as well. I've got some slides on that actually later that I'll show. So as you would imagine, there's so many things to do. It's very tough to stay focused and figure out what are the few projects we do first. So these are technologies that we have in our pocket, but they stop to a certain level, and really still looking for partners that, if there's a huge interest to bring out, then we're more than happy to work with you guys. So this is how the waveguide switch works. A typical waveguide switch, the way you think about it is it rotates, right? So the way it switches pathways is it rotates clockwise or counterclockwise, and that's how it switches the path. What we do is, again, using those small magnet actuation that I showed from that first micro relay, we would move the two states vertically. So one state would sit on top of the other, and we would just push it up and down electromagnetically, like you see here, to switch the different path. So we can create a 2x2 waveguide switch. This is what we were doing for that system, where you change the pathway of the signal. This is the first state, this is the second state. One sits on top of the other. and it switches up and down. Now you can change the path length. You can create phase shifters that way. You could create splitters, terminators. You could create switchable filters in this way. So a lot of, it's a very scalable technology in terms of all the different types of components you can make. And it's very small. It's 2 centimeters by 2 centimeters. And that's, of course, is looking at E-band. This is for E-band frequencies. Of course, that waveguide opening gets larger if you're going to lower frequencies. But yes, so that's another technology that we had to bear, and we can integrate with other waveguide systems. Now, this slide is just, again, an imagination slide, if you will. The reason why we were excited about the rectaxial transmission lines in our relays is we can create reconfigurable antennas with that, use the relays to change the direction of beams, and create cost-effective smart antennas. So this is some ideation work that we did that would combine our relay, combine the micro coax traces, and create high power beam steering. Now, not a lot, I don't have much to show for this, but again, this is just showing the potentials of Amalga and what Amalga can do, and what it can lead up to, right? So these are some ideas in terms of technologies that it enables. Other technologies that it enables. So I'm going to switch gears a little bit and talk about interconnects and interposers. Any questions thus far? All right. So one problem being in the packaging industry, if you will, and hearing some of the problems that they have, one problem we noticed was in terms of reliable interconnects, and then also interconnects that can handle high frequency. One pain we saw was with thermal expansion, CTE mismatch, and interconnects breaking due to the CTE mismatch between materials, as well as just physical reliability, these things cracking and breaking due to high stresses and whatnot. So we came up with a solution, which is essentially a flexible interconnect that is squishy, if you will. And the way this works is essentially it's a bundle of copper wires that have a plate on the bottom and that have on the top, so they can move left to right and they can move up and down, and that allows you to have a more reliable interconnection between your chip and your PCB. And I'm going to talk a little bit about how this works. Here's some of the pictures of some of the work that we've done. These can be very, very high density as well in terms of pitch. I'll talk about that a little bit later. But we do, in general, we do regular interposers as well. Let's see if that's the next slide. Oh, no, the slide after. So in this slide, this shows how we do it. So these are through a proprietary process that we use that we call anodic aluminum oxide templating. We take an anodic aluminum oxide wafer that has a bunch of little nanopores. And what we do is we grow that copper through those nanopores. We then release these wires from the AAO and bundle them up. So that's how we create these flexible these flexible posts, if you will. We call them compliant copper. So that's another technology that comes out from our toolbox through Amalga. Well, I guess that's all the slides I have. So I will mention interposers as well. We use anodic aluminum oxide to build very high density interposers as well, and we can create interposers with a variety of different shapes. We can create coax shapes in terms of the vias that allow for high frequency connections between chips and between chip to substrate, and all that fun stuff in terms of packaging. So yeah, a lot threw at you guys, but wanted to give some ideas and some capabilities that Amalga can do in the RF microwave realm of things. Love to hear your thoughts, love to hear your questions.
Can you say where the name Amalga came from?
Could you repeat that?
What's the name Amalga mean?
Amalga, yes, Amalga.
No, what does it mean, and where you got? How did you guys come up with it?
Yeah, so Amalga is short for amalgam, which and the reason for that is because it's really an amalgamation. It's an amalgam of different materials and processes. It's really an integration technology, if you will. It's a combination technology. That's actually why our initial name was Integra Devices, because we were creating very highly integrated devices. To give you an idea, and I talked about the monolithic limitations of the semiconductor MEMS approaches. When you look at a high value product, think of even, let's say, your car, a nice Bentley or Mercedes Benz. There's so many different materials that are associated with that car, right? You've got leather, you've got metal, you've got your rubber in the tires, you've got carpet, you got fabrics, you got glass, you name it, right? It's a bunch of different materials that they're able to manufacture and integrate these materials together. At the micro scale, there has yet to be a manufacturing technology that can do that. Silicon cannot do that. Machining, you're just machining out of a material. Amalga is really the first manufacturing paradigm that allows you to combine multiple different materials at the micro scale.
This is Jay. I came in a little bit late, but can you comment on the switching speed on the switches that you showed earlier?
Yeah, absolutely. So as I was telling Ukarsh earlier, we're not going to be able to compete with the switching speeds of a solid state device, which are typically microseconds or nanoseconds. We're in the microseconds. So it's three to 5 microseconds switching time.
Okay, and have you done any life testing on those switches for number of cycles?
Yeah, so and that's actually right now we're optimizing life cycles. Right now we're at 5 million. We're trying to get to 10 million. But safe to say right now that we'll be okay with even releasing these at 5 million life cycles.
So you also mentioned the medical application. Can you comment further on what sort of applications you're considering there, or what type of devices you're considering for that environment?
Yeah, absolutely. Let me give a couple examples on that. And just to give you an idea in terms of how we work as a company, a lot of the projects that we work on are through partnerships with industrial companies and medical companies. So they'll fund work to be done via a project, and we'll build that product and device for them to resell. And that happens a lot with the medical industry. And so one product that we've done is actually a zero power, completely biocompatible pressure sensor that's the size of an eyelash, to give you a sense of scale. So it's actually smaller than an eyelash, and that goes inside of the human eye to measure the pressure in your eye for glaucoma patients. Now, how it works, and again, this goes to show the integration of different materials at the micro scale, is there's a very small coil, and inside that coil, there's a liquid cavity and a little plug, and then a gas cavity that separates, that plug separates the gas cavity from the liquid cavity. And that's all surrounded by glass and then a polymer coating. Now, when the pressure changes in the eye, the liquid gets pushed through into those coils and pushes that plug into those coils. That plug is magnetic and thus changes the inductance of those coils. And then we ping it through an external RF reader to read the measurement of the pressure. Now, so that's an example of a product that we've done that leverages needs a lot of different materials, and it needs to be at a very small size scale, and it cannot have any active type of components. They did not want a battery. They did not want to have silicon in the eye. It needed to be fully biocompatible. So we do a lot of implantable work. We do a lot of drug delivery work. We do a lot of work in terms of combining microfluidics with electronics, so creating very small microfluidic components. We worked with Amgen to create a microfluidic inline pressure sensor for their drug delivery pumps to measure if there's a blockage or a leakage. And again, it's the ability to combine microfluidic materials and processes with with electronics, sensing elements, transducers, and make them smart as well, because we in that situation, we integrate the microcontroller. And again, these are very small footprints, 5 millimeters by 5 millimeters. The implantable sensor is about the size of an eyelash. So yeah, hopefully that gives you some idea. There's a lot. We do a lot, as you would imagine. It's over 15 years of work in different fields. Yeah.
Yeah, thank you.
Hey, Sourabh, Utkarsh here again. So if you go back to that slide which showed the E-band diplexer and other similarly, yeah, so what kind of frequency response, what are if it's a frequency diplexer, then it's going to be different frequencies that you're diplexing. So what kind of frequency separation and what kind of frequency response are we talking about?
Yeah, so with this diplexer specifically, let me try to remember, it's been a couple of years. So there was two bands, there was 71 to 76 gigahertz band that they were trying to isolate, and then an 81 to 86 gigahertz band that they were also trying to isolate. And what they were trying to do is transmit at one of those frequencies and receive at the other, and then have the ability to switch that. So let's say transmit at 71 gigahertz and receive at 81, switch it and then transmit at 81 and receive at 71. And the switching part comes through that waveguide switch, and the diplexer is what isolates those frequencies.
I see. Okay, thanks.
Mm-hmm.
And one follow-up question. So the target application, is that the waveguide, sorry, the cellular backhaul, is that one of the applications, or?
This application was actually for providing Wi-Fi globally. So shooting down Wi-Fi from these low orbit satellites. I'm sure you guys probably guess who it is.
Oh, okay.
There's a couple of big guys doing it. Yeah.
Yep.
Yeah.
Okay.
Mm-hmm.
Thanks.
Mm-hmm.
So just to remind you guys, some of you guys are muted. So if you have any questions, you probably need to unmute first. So are there any other questions for Sourabh at this time? Going once, going twice.
Are we getting a copy of these slides?
Yep.
Yes, so as I mentioned earlier, the lecture is going to be recorded, and the slides will also be made available to everybody who registered. So everybody here, you should receive an email in the coming days from me with links for both the video as well as the slides. Okay, so let's thank our speaker, Sourabh. Thank you very much.
Thanks for having me. It was a pleasure.
Yep, thank you very much. Stay tuned, everybody. We'll be posting links for upcoming events. Like I mentioned earlier, if you follow the hashtag, or if you're on the MTT mailing list, you should receive updates about our next events. Our next talk would be, again, third Wednesday of April, which from the looks of it will also be an online webinar, kind of similar to what we had today. So thank you all for coming and participating and making this happen. So everybody, so I'll just toss it back to Jay, who's our chairman. Jay, do you have any announcements or anything you want to say, or we can close out the events? I guess not. So with that, we'll close the events, and thank you everybody for coming, and see you next time.
Thank you.
Thank you all.